This section is on 10.3, finding the area of regular polygons. It follows the sections in which we found the area formulas of the basic structures. This area formula will work for all regular polygons. So that means that the side lengths and the interior angle measures will all be exactly the same. Two things that you have to know about a regular polygon before we can use the area formula is where the radius is and what the apothem is. The radius you are used to hearing in terms of circles, but polygons also have a radius. It starts at the center of their polygon and it goes out to the vertex of the shape. So this value here, the dotted one, would be the radius of this polygon. The apothem, which is another value that we're going to use specifically with this formula, has to do with the center of the polygon as well. It starts from the center, but it comes down and goes perpendicular to the opposite side. It also bisects the side. So this piece will be equal to this piece in any given regular polygon. The apothem is what we are going to use. I tell you about the radius because sometimes they give you the radius and expect you to find the apothem, or they expect you to know the difference between the two so that the apothem is the one that you use in the formula. Our formula for a regular polygon for finding the area is 1/2 times the apothem length times the perimeter. Perimeter, remember, is the distance all the way around the structure. So we have to find the distance around the structure and we have to find the length of that apothem, the length that goes from the center perpendicular to the opposite side. And again, this will work for all polygons. It doesn't matter how many sides it has as long as it's regular. So we use our formula. Our formula is 1/2 times the apothem times the perimeter, and we get right into example problems. Here they give us the apothem length is 6, so we stick that into the formula for A. And then they give us that one of our side lengths is 7. Since it's a regular polygon, all of our side lengths are the same. In this case, it's a pentagon, so there are 5 of them. So the distance around our structure, we would simply take 7 times 5 and get 35. So to find the area of our structure, we would take 1/2 times 6 times 35, and that would give us 105. The area for this formula, or for this shape, would be 105 square units. The next example that we're going to give that we're going to complete doesn't give us quite everything we need. We're going to have to use our previous knowledge and apply it to find what we need. This one, they do give us all the sides, and since it's a heptagon, 7 sides is a heptagon, we would take 7 times 5, and again, our perimeter happens to be 35 in this case. They again did not give us our apothem. They gave us the radius. We can use the radius, however, to find the apothem. Remember what I said, that when the apothem comes down, it creates a right angle, but it also bisects the sides. So since our side lengths are 5, the distance from here to here would be 2.5. That's going to allow us to do the Pythagorean theorem to find the length of our apothem. We would do 2.5 squared plus x squared equals 6.5 squared. When you solve that, you get x squared equals 36, which means your x is 6. Your apothem length is 6. In this case, we would take our apothem length of 6, stick it into our formula, and we would do 1/2 times 6 times 35. What do you know? The area of this one is also 105 square units. Sometimes they don't give us much of anything, and we have to use the clues about the shape itself. Okay, in this case, this is a hexagon. What's interesting about a hexagon is that when you take the interior angles of a hexagon, you get that remember that we do n minus 2 times 180 to get the interior angles. So we would do 6 minus 2 is 4, 4 times 180 is 720, and when we divide that by 6, each one of these angles is 120 degrees. We learned that way back in chapter 3. Which means these angles are 120, and when you draw in the radius, it bisects those. Okay? Not only does the apothem bisect the sides, but the radius bisects the angles. So that makes this one a 60-degree angle, which gives this the concept of a special right triangle. It is a 30, 60, 90 triangle. And if we know one side of a 30, 60, 90 triangle, we know all three sides because of our ratios. Remember that our ratios in a 30, 60, 90 triangle, remember that this is the shorter side is the x, the longer side is 2x, or excuse me, the hypotenuse is 2x, and the longer leg is x times the square root of 3. In this particular case, the apothem will represent our longer leg, the bottom will represent our smaller leg, and the radius would represent our hypotenuse. We can use what we know about this to find the lengths of the sides that we need. In this problem, all they give us is that our side lengths are 8, which then we know that our pieces down here are each going to be 4 because they're bisected. So to go from the shorter leg to the longer leg, we would take 4 times the square root of 3. So our apothem length is going to be 4 times the square root of 3, and that's what I have written here. Using the 30, 60, 90, our apothem is going to be 4 times the square root of 3. The other thing that we need to know to find the area is the perimeter. Well, it's 6 sides, and each one of them is 8 units long. So 6 times 8 is 48. Now, when you go to take and multiply all these numbers, 1/2 times 4 is 2. The square root of 3 is simply going to ride along at the end. So you'd do 1/2 times 4, which is 2. 2 times 48 is 96. So you would do 96 times the square root of 3, and then you'd do square units. This would be simplest radical form. If they wanted you to find it and round it to the nearest tenth, then you would actually take 96 times the square root of 3, and you would get 166.3 square units. Other shapes might create special triangles too, not only the hexagon. Squares, when you draw them in, will create 45, 45, 90. Equilateral triangles, when you draw those in, when you draw in the apothem, will create 30, 60, 90 triangles as well. So you can see how we're using those special right triangles to find the lengths that we need in order to find the area. The area formula itself, the 1/2 AP, is not difficult, but sometimes it's harder to find the A and the P values than it is to actually find the area. That concludes this lesson. Your homework is as follows.